Okay, I guess we're gonna start, and then maybe a few more people will trickle in as we go. So hello everyone, and welcome. Welcome again to the Emerging Technologies CAIDA event. This is a fundamental science stream. I will be hosting this session. My name is Leon Segal. I'm a faculty in the Department of Computer Science at UBC. We have 5 really wonderful talks this morning as part of the stream. And each talk is going to be 15 minutes, so I'm going to ask all our speakers and panelists to stick to that time limit. And because we're sort of limited on time and should end on schedule, we're not going to actually have questions for these talks, but rather I'll ask everybody to approach the speakers and gather afterwards and kind of hound them down and ask their questions at that point, but not during the session. Okay, so without further ado, it's a real pleasure to introduce Greg Mori. So Greg is a close friend and collaborator personally of mine for many, many years, but also a close friend of CAIDA. And he's a senior research director at Borealis AI and a professor in the School of Computing Science at Simon Fraser University. Greg has really unique perspective of being both an academic and industrial researcher all at the same time, and leading research labs in both. He also served as a computer science department head at Simon Fraser University, so also has a lot of administrative experience. And he received his PhD from degree in computer science from University of California, Berkeley in 2004. And since then has been working on all sorts of topics in computer vision and machine learning, kind of very, very broadly. So it's a pleasure to have him here, and Greg, take it away.
Thanks. And could you enable screen sharing for me? I'm not sure.
Are you not? Okay. Yes.
Looks good. Thanks.
Yeah.
Can you see my screen now?
Yes.
Great. And thanks very much, Leon, and really appreciate the invitation from CAIDA and everyone, especially Arin, who worked really hard to set up this event. So as Leon mentioned, I've been a professor at SFU for quite a long time now, 16 years or so. And about 2.5 years ago, I joined Borealis AI to lead their research effort. And in this talk, I'm going to give you a little bit of an introduction to Borealis and talk about research that we do there, specifically focused on temporal models. So Borealis AI is a 115-person team inside RBC. RBC, the Royal Bank of Canada, is Canada's largest private sector employer with about 85,000 employees worldwide. And the Borealis team, we're part of RBC, and we build AI-based products for financial services. Why did we do this? Borealis was created about 4 years ago. And as researchers, especially core machine learning researchers, Mark was mentioning, the landscape at the time, about 4 years ago, was very different from what it is today. People who were interested in careers in industry did not really have much choice in terms of Canadian companies or even locations in Canada where one could do the type of cutting edge research that we like to do. And RBC had the foresight to create an institute inside the bank that would provide opportunities for people who are interested in pushing the boundaries of what's possible with AI, but doing that in the context of financial services. So Borealis was created about 4 years ago. Started off with just a couple of people in Toronto. And at this point, as I mentioned, we've scaled up to about over 100 people across Canada. We do have labs around the country. In this day and age, what I would say is that Borealis has people who are connecting with each other on Zoom and Slack from apartments, condominiums, and houses across the country. And we do look forward to a time when we get back to actually working in these physical labs, but we do provide opportunities across Canada. We collaborate with top industry and academic institutions around the country. As I mentioned, we're a pretty young institute, but even in the short time we've been around, Borealis has published more than 50 top-tier conference papers, publishing regularly at the top AI venues such as NeurIPS, CVPR, ICML, ACL, etc. And through those collaborations, we work with academics and students in many institutes around Canada. So to give you a bit of a sense of what I mean by we build AI-based products for financial services, I'd like to talk with you a little bit about one of the first products that Borealis built. In collaboration with RBC Capital Markets, we built a technology called AIDEN, which is an approach for a problem known as order execution in capital markets. We publicly announced AIDEN earlier this month, and it's been something we've been working on really for the past 2.5 years. AIDEN solves a problem of what's called block order execution. It's typically targeted at RBC's institutional investor clients. These clients will come to us and say, today I would like to buy 100,000 shares of a security that's priced at, let's say, $20. So this is basically a $2 million trade. These clients will come to us and say, I'd like to do that over the course of today. Now, naively, if you went into the market and you placed an order that said, I'd like to buy 1 million units of this stock at $20, the price of that stock will go up, and our client won't get the best price possible. Instead, what our traders do is they use algorithms to break up that trade into smaller amounts. Maybe I'd like to sort of test the waters and buy a few units of the security now, wait a little bit, see how the price reacts, see how it moves over the course of the day. Now, if you're a machine learning researcher, you'll sort of notice that this is a sort of problem that would be very, very much useful if you're doing reinforcement learning. I could define a reward. For example, if I'm making a buy, I could define a reward that's based on the price that I obtain. A smaller price would be a higher reward. I have a set of actions that I can take. Those actions are things such as deciding to place orders, canceling previous orders, increasing the price of my order, decreasing the price of my order. Try to do this in the optimal way in order to get the best price possible for our clients. So RBC, together with Borealis, built such a system, and we called it AIDEN. It's a reinforcement learning-based system that learns how to execute orders in the market. It does online learning, so it learns from live market conditions, enabling it to adapt and change its strategies based on what's happening and new information that it acquires about how markets are behaving. It uses data that comes from across RBC's trading desks in Canada, US, and Europe, using all those large amounts of data to try to learn how to perform order execution better. Here's a quick video of what AIDEN looks like in action. The histogram over on the right-hand side shows a probability distribution over actions that AIDEN would like to take while executing an order. At one end of the spectrum, AIDEN can be very aggressive. Aggressive means, for example, crossing the spread, going after the current ask. Somebody's willing to sell a bit of this stock at a certain price, crossing and going over and taking that price. AIDEN would choose to do that if it believes that the current price it can get is likely better than something that would come later in the day. On the other end of the spectrum, AIDEN can be very conservative. Conservative would mean taking actions such as canceling previous orders that we have out, and you would do that if you think that now is not a good time to buy, I should wait until later in the day, I might get a better price. And the curves at the bottom track various types of metrics about how well AIDEN is doing at filling the order that has been requested to do by our client. So you may be wondering how well this works. AIDEN has been live for almost 2 years and has traded more than $80 billion worth of securities. It's been very successful at doing that. One measure of just how well it works is that in the early part of 2020, when the COVID pandemic was hitting North America, stock markets were going crazy, lots of very unusual behavior, high volatility. AIDEN was live throughout that whole period and traded extremely well. And again, I think this speaks a little bit to the power of machine learning and reinforcement learning, that instead of hard coding what strategy I should use, hard coding how I make decisions about what sort of actions to take in which environments, AIDEN will just learn on the fly. And it gets feedback, it gets a reward signal, it'll adapt, it'll figure out what types of strategies are better in this environment. And I think that many of you have heard exciting results in reinforcement learning for many years, from older days when people played backgammon with reinforcement learning through to recent times when people can defeat human champions at games like Go using reinforcement learning. These are extremely exciting things that have happened. Trading in capital markets, I think, is a sort of another level of difficulty when it comes to building reinforcement learning agents. If you think about a game like Go, playing against yourself, or sort of self-play to learn how to play a game of Go, it basically only costs you electricity. You just have to run models and train them against themselves. Instead, if you're learning how to trade in capital markets, exploration, exploitation, this involves real money. It involves actually making trades, actually buying and selling stocks, and being able to do that in an online fashion, yet still get high performance is something that I think is scientifically incredibly exciting. And with AIDA, we've shown that it's possible to take those machine learning algorithms that are great for game playing and other problems that exist and apply them to something that's a real world challenging task in a dynamic environment. Okay, so that's a little bit of a highlight of when I say machine learning based products, that's the type of thing that we've built at Borealis. I'm now going to transition into just highlight a few different bits of research that we've done that sort of push the boundaries of what's possible with temporal models. So at the bank, we have a large amount of data that come in the form of user transactions, whether these are credit card transactions or debit account transactions. We'd like to be able to use those to learn representations for our clients. These are useful for problems such as fraud detection or personalization. Thibaut Durand had a CVPR paper this year on learning user representations that take in sequences and use those to map to an embedding space that let you understand what a person likes and what they're likely to do in the future. So for example, if I see this transaction stream over on the right where someone goes to a restaurant Peckinpah, goes grocery shopping at IGA, then gets a cell phone bill for $50, I'd like to use that information to get a sense of what type of person this is. We built a model that takes that in as a history and embeds it into a space in which we can do computations such as probability for different brands for new purchases that somebody makes. As a quick sort of example of what this looks like, we have two different users here, and we can understand their preferences or what is most likely for them when it comes to clothing stores. The user on the right has a much more sort of flat distribution over different retailers are likely to spend at, whereas the one on the right, there's sort of higher probability of them shopping at what I would say sort of fast fashion or other retailers like H&M or American Eagle. As a second example of this type of work, we've done efforts into future event prediction. Nazanin, she had a CVPR paper last year on predicting of future events modeled by probabilistic versions of variational autoencoders for point processes. What this model is capable of doing is taking in an action history again, but an action history with timestamps. So for example, I could know that at time 1, the person shopped at a candy store. At time 2, the person shopped at a shoe store. At time 3, the person shopped at a women's fashion store. We built a model that can take in that type of history with timestamps and from there generate possible futures for that person. So for example, the first future says, I think that it's very likely the person will shop at a fast food store next, maybe 70% probability, as well as a temporal distribution over when that's likely to occur. So not only are we able to model what is going to happen next, but we can also model a continuous time probability density over when that event is going to take place. As an example, given a history such as this one here of grocery shopping, service station, hotel resort, fast food, hotel resort charges, this is the sort of thing that looks like perhaps a person is on a vacation or some sort of trip. We could generate that a likely sequence of next transactions would be something like variety store, and then a taxi limousine service. Similarly, this history with discount store, eating places, and clothing stores is suggestive of a user who is on perhaps a weekend shopping trip. From this, we could then generate a sequence of likely things that come next. For example, it might be a family clothing store, fast food restaurant, and grocery store as the next set of events. So this type of model, again, it's able to predict times and action categories. And this can be used in techniques, again, such as predicting futures, being intentive about what the user is likely to want next, as well as, again, looking at fraud detection and other techniques. All right, so finally, I'd like to highlight a NeurIPS 2020 paper that Borealis has produced on modeling stochastic processes in time using normalizing flows. So the task and motivation here, we're focusing on a task of modeling irregular time series. So previous methods, and there are many of them in literature, most recent are things such as variational RNNs or latent ODEs. These types of methods generally work on discrete time grids. This is visualized in the graph on the top right. The blue triangles denote observations that I've seen at particular points in time, again, potentially irregularly spaced. I've observed particular values of something that I care to measure. The gray dots denote a probability density that I could have over possible distributions over the underlying process that's generating these events. Previous methods focus on these discrete time points. In contrast, we've developed a method that views these as partial observations over time and directly model the distribution of functions. We actually build a model that can model these trajectories and a density over the trajectories based upon the observations that we have seen. In essence, what we're doing is we're modeling the underlying continuous time stochastic process. The way that we do this is via normalizing flow technique. Normalizing flow techniques start by a very simple base distribution and learn a method that will map that to the more complex distribution that I've seen. For these stochastic processes, we use a Wiener process, which is a very, very simple type of model that essentially is like modeling a random walk in continuous time. It makes very strong assumptions about independence and has a very simple model of this distribution. What we do is we build layers of normalizing flows that can map this simple Wiener process to the complex distribution that we have in mind. These mappings are invertible, which allow us to do very easy inference, interpolation, and other types of methods that we would like to perform. I'll skip over this for the sequence for the purpose of time, but as I mentioned, we're able to solve problems both in terms of density estimation. Density estimation is the problem of given a set of observations, I can ask how likely is that set of observations. I can also do sampling, which is I could create example trajectories through time based upon what I've seen. And finally, I can do methods in interpolation. So given these fixed observations, what's likely to happen in between them? And all of these can be done tractably because we have this invertible mapping that can take us from the complex distribution that we have learned back to the simple base distribution, the Wiener process, in which many of these operations are very tractable. I'll just sort of skip forward and conclude. We have lots of interesting experiments that show that negative log likelihoods of this model, the ones that we learn via our continuous time flow process, are superior to competing state-of-the-art methods on a variety of data sets. So in conclusion, I gave a quick intro to Borealis and told you how what we do is we develop AI-based products for financial services. I gave you an example of AIDAN, which is this order execution system that we've built based on reinforcement learning. Research is really at the core of the advances that we make at Borealis. A lot of this relies on temporal data. That's a very common data source in banking. And I gave some examples of the type of work that we've done. Building user representations, a CVPR paper this year, doing action prediction, one from last year, and how to model continuous time stochastic processes, a NERPS paper from this year. Thanks very much, and enjoy the rest of your day.
Thank you, Greg, virtual claps from everybody. It was great to hear about the core machine learning science and also the real application of those techniques that can really affect our daily lives. Obviously, the financial sector is something that we are dealing with on multiple times a day. So our next speaker in the series is pleasure to present Angel Chang. Angel is an associate professor in Simon Fraser University as well. Prior to this, she was a visiting research scientist in Facebook AI research and a research scientist at Eloquent Labs working on dialogues. She received her PhD in computer science from Stanford, where she was part of a natural language processing group working with Chris Manning. And her research focuses on connecting language to 3D representations of shapes and scenes, grounding of language for embodied agents in indoor environments and so on. So it's a pleasure to hear from you. Please take it away. Thank you.
Thank you, Lee. Thank you for the nice introduction. Let me share my screen. Okay, I think I'm sharing my screen. Can everyone see my slides? Maybe,
yes.
Hopefully. Okay, great. Yeah, so thank you so much for inviting me. Today I will talk about grounding natural language to 3D. As Neil mentioned, I'm currently at SFU, and I'm very happy to be there as part of this broader family of many excellent researchers in NLP, robotics, and visual computing. And today I'm going to talk about some work in my group where I focus on two themes. One is language grounding in 3D, and the other is interaction with language in 3D. So let's take a look at what can we do with language in 3D things. So imagine we have a little helpful robot, and I want to ask him to bring me my coffee cup. So in order to do that, the little robot needs to understand, oh, to find the coffee cup, he will need to first be able to locate it in the world, in the 3D environment, in order to bring me my coffee cup. So one project that I did with collaborators at TUM is to study the problem of 3D object localization in RGBD scans using natural language. And this work was presented this year at UCCV. And the problem here is that given a 3D scan of an environment, say using point clouds, we want, and a natural language description saying a black chair in the corner next to a table, we want to identify and localize which chair it is referring to, and actually provide the 3D bounding box of that chair. So this, in order to do this, we needed to first create a data set where we took 700 or so scenes from ScanNet, which was scans from the real world. And we basically asked mechanical Turkers to collect, to write descriptions for these objects that were previously annotated in this data set. And the annotators had access to this 3D interface on the web that they could use to look at the scene from slightly different perspectives, and then be able to say, oh, you know, write a description for the object. And using this process, we were then able to collect descriptions for objects that are associated with a 3D scene. So for instance, the description for this object would be, it is a dark blue couch in the center of the room, and this would be a long bar table behind stools. And we collected a little data set of about around 50,000 descriptions. And using this, then we can start to train a model that can actually identify and locate the 3D objects, and hopefully identify that this black office chair that's against the wall and facing the round table is this particular chair. And to do this, we developed a fairly, I would say, a fairly simple model that's kind of an extension of work in 2D, where we used a 3D object detector to detect objects in 3D, a language encoder that's based on GLUE, and basically this is just a language encoder. And what we wanted to do was we just wanted to see, okay, of the possible objects that are detected, which one matches the description the most, and then we'll just select that one as the most likely object. And this, I would say, is a fairly basic baseline method, and there's quite a lot of room for improvement. We have a benchmark that if people are interested in this problem, they can participate. But here are some descriptions that provided to our system, what we will predict as the object. And you can see that even so the system is able to work some of the time. For instance, this is a white chair, it is next to the bed and to the left of another chair. So it did identify, okay, it should be this a chair, but it's actually rather poor at resolving spatial relationships. And here I'm actually just showing some failure cases because I think they are a bit more interesting than the successful cases because they illustrate a bit of what's challenging about the problem. And the other example is the couches to the left of the coffee table and far from the wall. Again, here we see that our system here is able to identify a couch, but it's selecting the one that's close to the wall versus further from the wall, which is the ground truth on the right. And so there is still a lot to do in this area. And what I want to say is that there's just a couple of words I want to say here, which is that there is some benefits, I think, in working in 3D that's not, that you can't really achieve with static images. One is that you can have these long range spatial relationships that are not limited to a single view. So if we want to identify the chair that's furthest from the door, of course, if we take a top-down view of the room, maybe that's easy to do. But if you consider normal views that you would see from a first-person perspective, may be kind of challenging. The other advantage working with 3D can give us is that we actually have real-world sizes and that basically have meaning. So we can understand like chairs are bigger than coffee mugs, and that, you know, chairs, you know, if I'm a robot, I wouldn't be able to hold the chair in my gripper, right? A coffee mug, maybe. But there are some special challenges with working in 3D as well, in the sense that you have to consider that many of the spatial relations that we tend to use in language are egocentric or view specific, so that these relations are actually kind of maybe more appropriate if you had a first person view. So for instance, if we wanted to say chair to the left of the table, okay, maybe from this view, maybe it would be this one. But then if we were to switch our viewpoint, then maybe it could be this chair. So we do have to take those different views into consideration. The other issue that we face when working with 3D is that often these reconstructions, you can see this a little bit from this picture, is that it's not really necessarily very complete. And some of the objects, like even a trash can, which is medium-sized object, I would say, is maybe not very clear. And some smaller objects like mugs or pens would just be a blob. Okay, so that's a brief intro to work that we've done in localizing objects with natural language. So let's consider our little robot friend again. So now if I asked my robot assistant I told it that I left my notebook on the couch, can you get it for me? The robot now needs to actually move the pillows to find the notebook. So in order to do this, basically the robot needs to be able to interact with the 3D environment. And that's also another benefit of working with 3D, is that you can do interactions. And so the other area that my group works on is in the area of interpreting language for embodied AI. And what is embodied AI? In embodied AI, the idea is that we want to have an agent that can learn to perceive, act, and communicate with physical embodiment. Physical embodiment means that they are actually in some 3D environment, they're moving around, and so forth. And so basically, given our environment, by taking actions, they have different observations, and then based on their observations, they can then decide what actions to take. And in this embodied AI, you can also give the agent commands, such as navigation instructions of what to do. And so in embodied AI, often we use reinforcement learning to train these agents to act based on the sensory input. And the idea is we want to be able to navigate to objects or follow instructions that are provided in natural language. And this can be done in a purely reactive way, in the sense that the agent just sees something and it just does something. Or the agent can build mental representation with some kind of memory, or very explicit math representation. So in this year's New RIPS, we have a paper where we studied the different map representations for navigation tasks by having an agent that navigates to an ordered sequence of objects in your environment. So in this example, the agent needs to go to the red cylinder, then to the blue one. And so we studied the different kind of map representations, and we focused on egocentric grid-based maps. By grid-based maps, what we mean is that it's a grid, and egocentric means that the map is oriented so that the front is always a certain direction. And we studied maps with occupancy and object information. And we compared this oracle map where we have all this information against variants where we don't have a map, versus a map that we slowly build up over time as we travel from place to place, versus maps that are learned from neural features projected from egocentric views, versus a map where we use the egocentric views to predict objects. And what we found in our task is that if we have no map, it doesn't perform well as having some kind of map. But if we had the ground truth of what the occupancy and where the objects are, we can do even better. And so this, we hope, it would be a good test bed for people who are interested in studying embodied AI and map representation. And then the other thing I want to talk about is that we've also worked on, we are working on visual language navigation, where given language instruction, what we want to do is we want to actually train a robot to follow the instructions. And the idea here is that this is ongoing work. The idea is that what we'll do is we'll take our map representation and we'll predict waypoints based on the instructions. And then the agent can then use these waypoints to come up with low-level actions to allow them to navigate. And this is ongoing work. And this is just an example of an agent that would given an instruction, turn left at the bottom of the stairs and continue to the stools, how it would basically predict waypoints and follow the instructions. Okay. So this is all great, but so far you'll see that even my example where the little robot needed to move the pillow to find the notebook, maybe now the robot can travel to the couch, but it's still mostly navigating static environment. And for the robot to actually move the pillows, they need to be able to interact with the environment and do things. And so as to encourage research that looks at this interactive task, we basically have a white paper with a lot of other institutions, Intel, FAIR, AI2, Google, Berkeley. So this is both in industry as in academia, to basically encourage people to study this problem of rearrangement, where given a goal state and the current state, the robot needs to somehow figure out how to move the object to match the goal state. And in order to do that, the other thing that my group works on is building large-scale interactive environments for grounded language learning. And so I've worked on various simulation environments, the most recent of which is this environment called Sapien, where if you want to train a robot to, say, interact and push drawers, pull out drawers, you basically need to have all these models that are articulated, or they have parts that can move. And so we built this data set that have objects with parts that can move, so people can study this. And this data set has 2,000 or so objects, and it has a framework in C++ and Python that everybody can use. It's great, and it's really a step toward interactive robotics research with diverse set of textured articulated assets. But there are some drawbacks to this in the sense it's not arranged in scenes and it's still fairly small. And so another direction of my work is to be able to consider how do we push the effort out so that we can have interactive 3D environments at scale. And the idea here, so this is ongoing work, is to have large-scale reconstruction efforts where we can use 3D models to match real-world placement, include rich per-object annotations, and actually create these interactive articulated objects at scale. And to do so, we have a paper this year at 3DV, where we basically use a combination of program and 3D feature learning, where so that somebody can interactively write these programs while the computer offers suggestions and interactive grouping. And the idea here is then by defining rules on how these parts should articulate, and then having this be combined with interactive feature learning that can predict the joints and moving parts, then we allow people to kind of mix this program writing and machine learning using statistics, so to allow them to interactively annotate a large data set. Okay, and then once you have these articulated objects, you can put them in the scenes and you can do things with them. You can start to move them and things will be great. And then I just want to, I think this is my, conclude by saying that I think this area of having language plus learning about 3D representations and understanding and large-scale interactive environments will help us build these helpful AI assistants that can hopefully one day help us around the house. Okay, that's it.
Thank you, Angel. That was great. Great to hear about sort of our applications in robotics and so on. Again, virtual clap from everybody. And I'll, without further ado, I'll just intro our next speaker. And it's great to have Matt Teddy from Amazon with us here today. So Matt, from 2008 to 2018, was a professor of economics and statistics at the University of Chicago Wolf School of Business, where he developed their data science curriculum. Prior to this, and at Chicago, he also worked in a variety of industry positions, including as principal researcher at Microsoft and a research fellow at eBay. Matt left University of Chicago in 2018 to join Amazon as a vice president, and so it'd be great to hear from him about everything that's happening at Amazon and their engagement with machine learning.
All right. Thanks, Leonid. Okay. I think I'll start without slides at first and I'll bring them in later. So first of all, thanks to everybody for putting this together. You know, Kevin and Aaron and all of the others. It's fantastic. I was thinking about the topic and the kind of the subject that Mark started with, moving from academic work and core research in machine learning to industrial applications and actually building an industry around AI. And, you know, that's been a lot of what I've done and I've learned. You know, I started out as an academic. I kind of, you know, kind of like Greg, I was doing both for quite a while. And then now I've, you know, fully stepped away from, you know, my former academic career in mathematics and statistics to now where my job is building software, right? So I have an organization with teams that build software to automate our business and operations processes at a massive scale. So, so one thing I'll say about that is it's super fun. You know, I was kind of reflecting on it when we're talking here with a bunch of academics and seeing some old friends. And I'm also, you know, in my day job, staring at the 5 busiest days of the year for Amazon starting tomorrow. So, so it's kind of a good clash of my worlds coming together here. The other thing that I wanted to talk about, and you know, my talk's gonna be pretty high level, but the point I want to get across are some lessons that I've learned about what it takes to really build an industry around AI and an industrial set of industrial applications around AI, and what you need that is above and beyond the core research that that you might typically get out of academia, and the roles that perhaps non-traditional AI departments outside of computer science need to play in order for us to actually use AI in the decision-making applications that are important for the sort of things that I do at Amazon. So when we talk just very briefly about the sort of things we build at Amazon, I run a team that automates decisions. Now, that's very vague, and it can refer to anything, and it does refer to stuff we do from pricing to logistics to what we refer to as discovery. So how you as a customer might interact with Amazon, you know, the search and the browse experience. To a lot of our work is really all aspects of the marketplace where it's not customers interacting, but vendors and sellers. So the people who sell into Amazon, who use Amazon as a store, either in a retail relationship or in a relationship where they post their own goods on the website, and we facilitate logistics for them. So when I talk about AI and the sort of flavor of AI that I work on, I actually invert the I and the A, and I think about intelligent automation, and I anchor a lot of what we do at Amazon and what my team does on automation. So, and automation doesn't need to use machine learning, right? It's an old concept. It's just the application of machines to tasks that would otherwise be done by humans, or perhaps were not even possible because you couldn't get enough humans together and organize them to perform these tasks. So like I said, automation is an old idea. You have everything going back to weaving looms, you know, then to factory lines in the 20th century, production factory lines for cars in particular. And then you get into things like ATMs and autopilot and all of the sort of, you know, automation that we encounter in our day-to-day without even thinking about it. And now you're moving into a whole slew of ML-based tools, right? I think the Aiden example that Greg talked about is a great automation example, right? From my previous work in finance, I know exactly what Greg was talking about, which is, you know, the most important thing when you're trading at an industrial or at an institutional scale is how you, it's not what you buy, it's how you minimize costs on the trades, right? It's also what you buy, but that one's a little bit more obvious, whereas there's a lot of money to be made on how you minimize costs on the transactions. And I love that example with Aiden because it shows that you can automate what a lot of quant analysts and qualitative analysts were trying to do in a more ad hoc and very manual manner, and probably not doing as well as Aiden managed to do in the pre-ML era. Okay, so when you think about moving to automation based on AI, or based on machine learning, I actually think Mark said this really well. You're talking about programming automation from data, okay? So you're building intelligent automation tools that derive their decisions and their actions from past data, okay? So that's what makes it, sorry, that's what makes it ML based. Everything we do in practice is not just ML based, it involves reinforcement learning. So I've yet to come across a real compelling intelligent automation example where you don't have to be actively accumulating new data and building systems that are self-adapting and self-learning. So they're gonna get their own data, they're gonna see when things change, and they're gonna adapt their actions and their decisions. In other words, adapt their automation as a result of that new data. Greg mentioned this as well, but the importance of this type of intelligent automation has really been reinforced during COVID, right? So when things hit the fan and supply chains froze back in March, when COVID first started to move and spread and expand, the automation systems that were based on ML and data, they broke for a little bit, right? Things kind of, seized up and didn't work so well. But without us actually having to do anything, those automation systems that were based on machine learning and data were able to adapt and respond and move and adjust to this new normal, whatever that new normal was, and adjust to the several new normals that have come since March. Whereas any of the automation that was based on hard-coded logic rules or heuristics or required a bunch of manual work, so humans with instructions who were working within a prescribed system, all of that stuff needed to be rethought, re-architected, ripped out, and rebuilt from scratch. And so it's a very, very expensive, very slow process to get those things back up online when something like COVID hits. Whereas the stuff based on machine learning, the intelligent automation, is able to fix itself. So the whole COVID breakout was a real emphasis for me on the importance of this type of automation. And so now, here's one of the points I want to make. I'm going to try and share my my screen here. See if I can achieve this. All right. So you should be seeing it there. I don't have fancy slides. It's just a picture of a bunch of boxes. But this is kind of my point here, which is the systems where I need to work on automation and where we're building automation are extremely messy. Okay, and they're not easy to characterize as problems that you might be able to solve with computers and with machine learning. So to put it another way, without belittling the importance of the machine learning and the reinforcement learning, we're big investors in research. I have a lot of PhD scientists on my team, and we spend a lot of time on this. But frankly, it's kind of the easy part, figuring out the best algorithms once you frame the problem. And that's the hard part. The hard part is taking a messy business or operations problem, characterizing the system that you're working with, and breaking it down into a number of prediction questions. And prediction questions are the sort of questions that you can then start tackling them with mathematics and machine learning and reinforcement learning. So to give you a little bit of an illustration of what I'm talking about here, look at, Mark and Greg, I think, mentioned this as well. A lot of the advancements that have been made, which are extremely impressive in terms of reinforcement learning systems being able to play games, be that, AlphaGo or backgammon way back in the day, or video games like Miss Pac-Man, which is what I have up here. And this is not an Amazon example. This is from one of my previous employers. Actually, it's out of Montreal. So it's a Microsoft research group in Montreal. And essentially it's the thing that you're familiar with from the news, which is you can train a reinforcement learning system to play a complicated video game. And in particular, the way that this system works, the Miss Pac-Man system, is you have, you look at the board, I guess it's called, where Miss Pac-Man goes around and tries to avoid being eaten by the other things. And each cell on that board, each little square where there's a dash on the thing, is a single reinforcement learner, okay? So there's a single prediction problem. And so what they've done is they've taken this problem of optimizing and playing the game of Miss Pac-Man, and they've broken it down to, I think it was, 100 or 200 odd individual machine learning problems, prediction questions, which are interacting. But each of those prediction questions is pretty straightforward. It is, when Miss Pac-Man arrives on this cell, given the situation on the rest of the board, which direction should she go, okay? And so the reason that you're able to use reinforcement learning to solve a complicated game like Miss Pac-Man or much more complicated games like Go is that you've been able to look at the rules of the game, look at the board, and break the problem down into a bunch of prediction tasks that you can then attack with machine learning and reinforcement learning. Now, the scenario I'm in is the boxes, right? That's why I have this slide. I don't have the rules of the game, right? I have a situation where I might have, well, what I do have right now, a bunch of inventory clogged up in ports around the world. Those of you that follow global shipping, you know that the West Coast ports are extremely congested right now. And in China, we're low on containers. There's all sorts of issues due to the fact that the shutdown in shipping during COVID and then the rapid spike back up. Or I might have a problem where I have boxes piling up somewhere, or it might be something less dramatic than that. And I have to figure out, how do I most optimally figure out prices to align incentives between sellers and Amazon and customer and make sure things that, get where it needs to go through market mechanisms. And so all of this is to say that when we meet a reinforcement or when we meet a problem, we don't meet a problem where the rules of the game are explicit. And so you need scientists, you need technologists and engineers who can think about these business problems, these operation problems, and characterize them as systems and break those systems down into a bunch of constituent machine learning problems. And then that's where you get, the computer science PhDs and people with expertise in statistics and machine learning to start to go to town on those problems. And so the message that I want to get across is that when you think about an industrial AI base, you really need to invest in the domain expertise that's adjacent to the machine learning, that's adjacent to the artificial intelligence research. And so you need to find the people. On my team, it's largely economists, but also operations researchers and people with expertise in logistics and such. You need to find those people, have them be able to work together with the computer scientists and figure out what the right way is to take problems that are messy, abstract, boxes piling up, containers getting congested, things like that, and break them down into things that can be solved through, break them down into prediction tasks, okay? And then you can deploy ML to optimize on those prediction spaces. So at a very high level, that's what we do, right? So we have problems. We work with people. We're a very wide tent team. I do have a large team, or a relatively large team in Vancouver. We have people with PhDs ranging from economics to physics to math to computer science. We have engineers. We have people from all different backgrounds, and we attack problems that might not look on their face like something you would be able to solve with AI, but we start thinking about how would we automate this space? How would we build automation in here? And then we work our way down to a bunch of computer science, machine learning, and reinforcement learning tasks. When you're encountering this stuff, so on the left here on the slide, there's actually a pretty decent article The Economist wrote about us probably a year ago. It talks about our low-key approach to AI, which I don't know if that's a good thing or a bad thing, but it is what we do, right? We go in, we find these things, we break it down, and we then attack it with machine learning. A couple of the things I would emphasize for the researchers and people in the room who are thinking about what areas to work on. One thing is we spend a lot of work on causal problems, so causal inference. And the reason for that is when you start breaking these problems into things that need to be automated, you typically need to understand why things have happened and not just find patterns that predict a future that is mostly like the past. So the stuff, Kevin works on this, others at UBC are working on these sorts of things a lot. There's a huge amount of importance on causal inference and the type of systems that we are working with. And then the other one, because I think, often in academia, we talk a lot with the science faculty. And I think at UBC and with CAIDA, it's great. And at SFU as well, you have a big interaction between the engineering schools and the science schools and the science department. And that's a big thing. That's where I spend a lot of my effort at Amazon right now, is trying to think about machine learning as an engineering discipline, right? So kind of how Mark put it at the very beginning, think about machine learning as a type of engineering that uses data to create programs. And so you really have to think seriously about your input and your output. Again, as Mark said, you have to think about platforms, so models that are work for multiple tasks, and sets of machine learning infrastructure that are good in general, not good for a specific task. And then also spending a very, very high percentage of your time focusing on optimization efficiency, which when you think about it, when you come to machine learning algorithms that need to be self-adapting and self-learning and self-adjusting, optimization efficiency is actually operational efficiency. And that's when you're running things at the scale that we are, that is of first order importance. So that's the message. Thanks. And again, thanks to everybody for organizing this. I'm really excited to meet all the people here.
Thank you very much, Matt, and thank you for those perspectives. Acknowledging that we are running somewhat late, I will just go ahead and introduce our final speaker for the session. It's Frank Wood. Frank is a close friend and colleague. We share the same academic ancestry. Frank is an associate professor of computer science at the University of British Columbia, and as Canada CFAR AI Chair in Miller Institute in Montreal. Frank has had a very decorated academic and entrepreneurial career. Prior to joining UBC, he was faculty at Oxford and Columbia. His primary research areas are probabilistic programming and probabilistic machine learning. Now, before I pass this on to Frank, just one last bit of information, because this is our last talk of the session, and I also have another engagement that I will need to run to in a few minutes. I want to preemptively thank everybody for attending this session, and just mention that after Frank's talk, everybody should proceed to gather for the rest of the day's agenda, which includes the poster session. And Galora, who is helping with organization, will also be here to direct everyone at the end of the talk. But I'm super excited to have Frank here and to give us his perspective on machine learning. Frank, take it away.
Thanks, Leon. Can you hear me okay? And see the slides all right?
Yep.
Awesome. It's good to be with you all, and thanks for organizing this. It's bound to be fun. So yeah, I'm going to talk about deep probabilistic programming, particularly through the lens of case studies and hopefully highlighting industrial opportunity along the way. So I only have 15 minutes. I would love to regale you with the story of the time that I had dinner with Ben Stiller in the apartment of the owner of the New York Mets on the Upper East Side of Manhattan, in the same building where Barack Obama was, and the secret security, the presidential detail had shut down the block. Okay, whatever. That would be a fun story to tell. It's actually a true story too. Ben's a lovely guy. But I put this here to remind you, put Ben here in his Zoolander guise to remind you that there is some confusion about what exactly a model is. So that word has been used quite a lot. I want to make sure that we all understand that there's at least there are at least a couple of different ways of thinking about what a model is. And to me, very specifically, a model is a joint distribution. In particular, it's a joint distribution, usually with some parameters theta, that relates stuff that you can observe, and that's going to be y, with stuff that you can't see but want to know, and that'll be x throughout. Okay, and usually when we write down a model, and this is different to the notion of model that Mark talked about in his supervised learning section, and a little bit different to what Matt was just talking about now. But usually when we talk about probabilistic models or joint probability distributions, we break them down into different parts. One of them is the likelihood, which is how what we see gets generated, and the other one is the prior, which is what stuff in whatever world we're considering is allowed. So for me, a model is not a conditional distribution that you fit with some sort of supervised learning, but is instead a joint distribution which you may or may not learn from data. And again, I'm going to use model and joint distribution interchangeably, and I'll talk about likelihoods and priors a couple of places. But the problem with a model like this, and what you want to do with it, is that you know, it's nice that you have such a model, but you need to be able to operate in it. In other words, you are going to be able to observe some stuff. We're going to be able to observe some, you know, some Y, and you'd like to get information about the stuff that you want to know given that observation. And you know, Reverend Thomas Bayes established a relationship linking the model and basically showing how to compute within a model to get what you want. You want information about stuff that you can't see but want to know. This is going to be the distribution of the latent variable in your model given an observation. And this is related to the model, which here is in the likelihood times prior form. And you know, there's some names given to these things, and you know, posterior probability of latent variables given observations and that sort of stuff. And there's an evidence here, so on and so forth. But the point is that we'd like to be able to compute using our model, which is a joint distribution, to give us information about stuff we want to know but can't directly see. Okay, fine. Now I'll just point out that you know. Everyone on the panel, and probably most of you who are listening, know that Bayesian inference it's the right thing to do. But unfortunately, it's gotten quite a bad rap for quite a long time, which is that it's too computationally inefficient. That evidence thing, you know, hides a very, very complicated computation that needs to be done. You know, building Bayesian models and deriving stuff for inference is really, really hard. But what I guess one of the main messages that I'd like to put out there today is that we are, I think, very near the beginning of the kind of explosion that we saw in supervised learning when compute caught up and languages and tools were developed like PyTorch or TensorFlow or these kinds of automatic differentiation packages. We're near the same kind of thing for Bayesian inference and unsupervised learning writ large. So my group, the Programming Languages for Artificial Intelligence group here at UBC, has been historically, through the time that I was at Columbia and at Oxford, so on and so forth as well, been at the very forefront of the development of tools and languages for automating Bayesian inference, leading from sort of early work in probabilistic programming that led to systems like Anglican and Stan, to modern deep probabilistic programming systems like PyProb and Pyro and Edward and TensorFlow probability and these sorts of things, which address a spectrum of computational and Bayesian inference requirements, ranging from, you know, whether you have a model or you need to learn the model, or when you're doing inference, whether you want to do sort of slow one-shot statistical style inference, or if you're doing more AI type things like those which I'm interested in, you need to be able to do fast repeated inference. Now, for those of you who are old enough and have been in machine learning long enough, you will recognize this, although this is the best picture that I could see for it, which is that my friend Jan LeCun would go around, you know, almost 20 years ago now, and give these talks where, you know, he would take a camera and put it out in the audience and show the power of convolutional neural networks and give demonstrations, and this is really cool, and so on and so forth. And he was doing this in the time of, you know, the ascendance of logistic regression and support vector machines and kernel methods and these sorts of things. And he persisted because, you know, there was evidence that, you know, you could do very, very cool things. So I realized that my talks are sort of, and I kind of was annoyed by those talks because there wasn't a lot of technical meat in those talks. But in retrospect, I realized what he was doing, which is to say, hey, look, pay attention. There's actually something here. And I think that you know, that's kind of where I'm going. And I'm not comparing myself to Jan LeCun per se, but the message that I'd like to get across is that, you know, actually the cutting edge is somewhere different, right? And the kinds of things that we can do are pretty cool now. So let's go through some case studies where we're going to look at different choices of what the latent variables are. The stuff that we want to know is X, and we're going to look at some different cases for what Y is, and we're going to what we can see is, and we're going to look at some different cases of what the model will be. And you know, I don't have time to go through the technical details, obviously, but what you should take away from this is that the same kind of tool chain, the tools that we were developed, that I pointed out, PyProb and Pyro and you know, these sorts of deep probabilistic programming systems and techniques are able to do some pretty amazing things now. And it's getting close to the time, I think, when people should start paying attention. So many of you have seen this example. This is the Atlas detector on the Large Hadron Collider. A long time ago, I'd say, 6 years ago now, in my office at Oxford, I said, well, let's just go ahead and demonstrate what we can do, okay? So here, there really is a latent variable problem. There's something that you can't see, but you want to know. There's the high energy interaction of particles inside of the Atlas detector, for instance. And there's literally no physical way that you can observe what's going on, but you care a very, very great deal about what's going on, because that's how you answer questions about physics and the fundamental nature of the world. So a model here is the standard model and an Atlas detector simulator. By the way, these really only exist in terms of very, very large stochastic simulators and huge code bases. So that's, I guess you can't see my cursor. I don't have a cursor control. That's on the left-hand side of the screen. And what you can see are sort of energies deposited in the detector. Okay, but what you want to know is what interaction gave rise to the signal that you can see. So the first example, and the largest scale example of deep probabilistic programming amortized inference, is work that appeared in both NeurIPS and Supercomputing 19. It took a little while for it to be accepted. Actually, we put this in 2017 or something like that. It took a very long time for people to understand what was going on. And I think still it's hard for people to really grok what's happening here. We can now learn using the tools of actually supervised learning, basically, amortized inference posterior approximations within the simulator QPhi, which allow us to very, very rapidly compute the posterior distribution of parameters or of latent variables of interest. Here, the particle types, momenta, so on and so forth, in basically a feed-forward computation from the detector outputs. Okay, that's pretty cool. So this is the first case study, okay? So the X here, the thing that we want to know are particle types and momenta. The Y are the Atlas detector responses. And the model came in the form of a very, very, very large, super highly refined simulator written by, thousands of people over decades. But the same kind of technology can be applied all over the place. And I think another point that I'd like to make as I'm going through here is that, when you see the breadth of the kinds of things that we're working on, you might think, oh my goodness, how the heck can they possibly do this? And it really is the development and maturity of the tool chains that we're talking about. Other people have seen this. This is wing stress testing on a modern composite jetliner. And this has to do with baking muffins, in the sense that if you take a composite part, and you put it in basically an oven. Here I show a part on a support, a two-dimensional cross section, and then a one-dimensional cross section. In one of the first and arguably most interesting industrial collaborations that my group has had in British Columbia, we looked at a simulator written by this UBC spinout called Convergent of composite curing processes. So in this one-dimensional slice of a part, excuse me for going back, the blue dotted line there, the simulator is a model of the part temperature at all depths in the part over all times. And of course, what you want to know is whether or not the center of the muffin is well cooked, but you can't see that except by, destructively, burrowing into the part, basically thereby destroying the airplane wing. But using the tools of amortized inference and deep probabilistic programming, we can build a rapid inference artifact which gives us access to an approximate posterior of the latent variables of interest, X, the temperature in the middle of the part, indicated by the thermometer here, the temperature in the middle of the part at a particular critical point in time, given observed temperatures on the surface of the part and in the air in the oven, basically, okay? And what's kind of cool about this is that not only can we do rapid inference, but we can also actually learn a surrogate model of the simulator so that not only does our approximate posterior actually look, if you see there's like a little uncertainty here, and this is flashing, this is actually the posterior distribution over temperatures in the part given the surface measurements under the simulator on the right, which is a slow, laborious, old school Bayesian computation, and via inference in a learned surrogate model using a deep neural approximate posterior. Okay, so basically, the simulator is 90 times faster. Inference is fast enough that you can actually use this to do effectively virtual part inspections while the parts are being processed. Oh dear. Okay. So I think I'm way out of time. I'll skip over a bunch of stuff because I think I just completely destroyed time. So let me go to another use case of the techniques that we're talking about, one that we're looking at right now. So in terms of industrial applicability, the same kind of latent variable models can be applied to multi-agent systems, to computer processing, joint predicting the joint runtimes of large clusters. Basically, whatever latent variable model you want to put together. Now we have the tools to express posterior inference in those models efficiently via programming languages and computationally efficiently using the tools of deep probabilistic programming. So many of you are aware that there is a spin out that we've chucked out of my lab called Inverted AI. And one of the first things that we're looking at, basically the application that we're looking at for demonstrating this kind of Bayesian inference, deep probabilistic programming, posterior uncertainty, rapid amortized inference, and model learning, which I won't have time to discuss, is in the space of autonomous driving, and in particular, the joint prediction of multi-agent systems. So here we have a top-down view of some real traffic moving about in the real world, and as you see, the vehicle is changing from dark to light color. This is this is conditional. This is posterior predictive inference about the forward trajectories of multi-agent systems predicted using a learned model using amortized inference in real time using tools and techniques from deep probabilistic programming. Here's some examples of sample diversity from such a model. And the point of this is that we can use this kind of learned model in training reinforcement learning agents that drive not from top-down views, but from front views as well. 15 minutes goes really fast, so I will skip over all the really cool stuff unless I have time to take questions. Here's another, this is the latest, greatest state-of-the-art amortized inference, predictive inference in conditional neural processes that's come out of the lab. Love to tell you more about it. The point is, we have another case study where the tools of deep probabilistic programming and Bayesian inference are applicable, useful, easy to deploy, and produce world class results. Anyway, so I know that Mark and Matt have, and I missed some of the other earlier talks because I had to do kid drop off this morning, but I know that one of the subjects that's been on offer is engagement models between industry and academia. And I engage in all of them in terms of my tax-funded collaborative research projects and direct funding and consulting and so on and so forth. But my group is really headed towards AGI. This is our goal. And along the way, I'd like to just point out that beyond sort of deep learning models and standard supervised learning applications, there are a large number of sort of fundamental research results that can be both monetized and exploited, particularly locally. And I'd like to say that BC is getting there, but we're still not where we are, where, say for instance, the US model works, in particular, California. So, there you have a bunch of, academic research labs that universities that funding programs that explicitly support the creation of what were local startups in the Bay Area. They were startups. They were not, Amazon Research Labs or whatever that came in and poached local talent. They're startups that then grew and came to dominate the local economy. And I think that we've got the beginnings of the makings of such a thing here, but not everything has been wired together correctly yet. And I think that locally we have a lot of soul searching and work to do to ensure that we are not just a body shop for the rest of the world, but instead build an economic engine built on spinning out companies and technology from strong local universities with appropriate risk insensitive government programs and local investor activity. So I think that's it. I think that's all the time that I have. I think I'm way over time actually, so I appreciate it. Thank you.
Many thanks, Frank, for the very informative talk. We all enjoyed it. And also I wanted to once again thanks all of the panelists for the great presentation. All the virtual claps for you guys. Okay, now I wanted to ask all of our attendees to move to the main lobby because unfortunately because of our time limits, we don't have any Q&A for this session, but you can always find the panelists in the networking event and ask your questions there. Please join me in moving to the main lobby on the gather, basically for the student poster session. And the students are available next to their posters. You can ask and discuss their basic projects with them. Always use the key X to interact with the objects in the gather. Thank you all. See you in the gather.